Welcome to solverfy.
Okay, in this problem, we have a hydrogen atom in its n equals 1 ground state. We're asked to find in part A the kinetic energy, potential energy, and total energy of this ground state for an electron orbiting simple nucleus, hydrogen nucleus. Part B, we're asked to show this relationship that the potential energy for any arbitrary state level is equal to -2 times the kinetic energy of that level. We're then asked to show the relationship that the kinetic energy of a particular level is simply the negative of the total energy. So we're going to need various aspects of the Bohr model for this problem. We're going to need the kinetic energy for an arbitrary level, 1/2 mv squared. V is dependent on the energy level. We have that expression in terms of various known quantities. Similarly, we can use the potential energy for an electron orbiting a proton at some radius Rn away, and we can express Rn in terms of known quantities using Bohr model. These all depend on the n index, and we have the total energy in terms of known quantities and n. So let's get started. Let's jump into it. So part A, we have the ground state n equals 1, so we simply need to take our expressions for k, u, and e and make n equals 1. That should be relatively straightforward. So in this case, for k, we have 1/2 m v1 squared. Combining the k expression with v, we can end up with 1/epsilon naught squared me to the 4th over 8 h squared. Similarly, u1 is equal to 1/4 pi epsilon naught e squared over the Bohr radius for level 1 squared. Setting n equal to 1 in the Bohr radius and combining with this expression for potential energy, we're left with, -1 there. We're left with -1/4 pi epsilon naught as before, but the 4 pi cancels out. So we're actually left with 1/epsilon naught me to the 4th power over 4 h squared. And finally, for the total energy, E1, we have -1/epsilon naught squared me to the 4th power all over 8 h squared. So all we've done is we've combined the velocity v1 with the kinetic energy. We've combined the Bohr radius with the potential energy. We've eliminated n by setting it equal to 1 for the ground state, and we have all of our expressions for the ground state. Done. Now for part B, we can, before we do part B, we can get these numerical expressions. If you've seen the alternate version for energy levels, you may not be surprised to know that after inserting the electron mass, electron charge, Planck's constant, electric permittivity, you see that the first energy level is -13.6 eV. That's usually simplified in this expression for energy levels in the Bohr model, so you may not be surprised by that value. Similarly, K1 is simply 13.6 eV, and U1 is 27.2 eV. I should say -27.2 eV. So those are the numerical values. So you already see that the relationship that we're going to prove in part B and C holds for the first energy level. We're going to show it for arbitrary n. So we actually could look at these general expressions. So for the first part, we're asked to show, or for part B, we're asked to show that for any arbitrary level n, the potential energy at that level is simply -2 times the kinetic energy at that level. So we could simply look at the general expressions for un and kn. For un, we have -1/ε0 squared me to the 4 over 4n squared h squared. And this is simply combining the Bohr radius with the potential energy equation. Similarly, with kinetic energy, we have 1/ε0 squared me to the 4 8n squared h squared. This is by simply combining the electron velocity for an arbitrary level n with the kinetic energy expression. And it's clear to see once you pull all the constants away that we have a 1/4n squared and a 1/8n squared. Thus, these two are in fact related by a -2 factor. Similarly, we can show rather trivially that En is in fact the negative of the kinetic energy. Once we see that the full expression for an arbitrary n level of the total energy is 1/ε0 squared n e to the 4 or m e to the 4 8n squared h squared. And you can clearly see that this is in fact the negative of kn. So that's it. It's relatively simple to show because we have so many constants we can pull away. The relationships become clear, and that's all we're asked for. So thank you.